everyone, Mrs. Nelson here. Have you ever wondered why you always have to wear a seatbelt every time you get into your car? So let me put my seatbelt on. I'm gonna show you why. The reasons why you always have to wear your seatbelt. Check this out. Hi, Mrs. Nelson here again. So I'm driving in my neighborhood and oops, there's something on the road. Uh-oh. Why did I lurch forward? Why did I move forward? When I initially was moving, and then I pressed on the brake. Well, that's gonna be our lesson for today. So here are our learning goals. First, to differentiate between mass and weight. Second, to describe and explain laws of motion. And third, to identify action and reaction pairs. So let's start with the Newton's first law of motion, otherwise known as the law of inertia. So a body at rest, correct. You're probably going to have to continue that statement because you remember it in middle school. A body at rest remains at rest unless acted upon by net external force. What is this net external force? It is the sum of the forces acting on the object. So there's another statement. It says if a body is in motion, it remains in motion at a constant velocity. So there are two states of motion that's been mentioned in the law of inertia. One that is at rest and one that is in motion. So whatever the state of motion of an object, unless acted upon by an outside force, that state of motion will continue to proceed. So here in our illustration right here, we have a van and there's a ladder on top of it, unsecured. So what happens when the van abruptly stops? The ladder continues to move in its state of motion. Because what is the original state of motion of the van and the ladder? Correct. They are both in motion. So what happens? The ladder will continue to move in its original velocity. What happens to the van? It's because there is a net force, so it didn't, the motion of the van stops. All right? So let's define some of these words. That's very important. First is the net force, and I've already talked about the net force. The net force is sometimes written as like this. So if you are taking statistics right now, you see the sigma, which means the summation of the F. F, we talked about F in the previous video, which is the symbol for force. Okay. Mass is a measure of inertia. You probably learned that in chemistry, and your definition probably is the amount of matter that is present on an object. And it is measured in kilograms. In the unit, the SI unit for mass, by the way, is kilograms, kg. Now, what is inertia? And why is it that mass is a measure of inertia? Inertia is the tendency of an object to resist changes in motion or to resist changes in velocity. Okay, so say for instance, we have here a van, right? And this van is bigger than this car. To say it right, using the concept of mass, the van will have more mass than the small car. So which one will have more inertia? Correct. The van will have more inertia. Why? Because this van will have more tendency to resist changes in motion than the small car. And the car has less inertia. So in other words, the lesser the mass, less mass, means the lesser would be the inertia. All right. So More mass means more inertia. How about the difference between mass and weight? We just said mass is a measure of inertia and is measured in kilograms. And weight is a force acting on the object due to a planet's gravitational force or due to its gravity. So we say that weight is a force. So, in other words, it is measured in Newton, or simply we use the symbol N. So, those are the three important things that you need to know when we talked about inertia. Now let's look into the two things of what will happen if forces are balanced for an object at rest and for an object in motion. So if the forces are balanced, let's say for instance we have 5 forces acting on one object. Okay? So there are 5 forces. If these 5 forces acting on that object that is initially at rest, then that object will continue to stay at rest. Okay? So when that object is at rest, we say that the velocity would be 0 meters per second. And of course, the acceleration is 0 meters per second squared. Therefore, that object will remain at rest. How about when it is initially in motion or moving at a constant velocity, for instance? So if it's moving at a constant velocity, then that object will not be accelerating. Because if it's accelerating, then there is a net force. So Newton's first law talks about forces being balanced. Newton perceived that if forces are balanced, regardless of whether how many million of forces acting on it, if they balance each other out, or if the sum of all the forces is equal to 0, then that object which is at rest will stay at rest. That object that is in motion will stay in motion in the same speed, same constant velocity, and same direction. So those are the two important things about the law of inertia. So we've been talking about object at rest, which has a 0 acceleration, and object at constant velocity, which is also having zero acceleration. So we said these are the big things, big ideas about Newton's first law. If the forces acting on an object are balanced, then the net force is 0. So the first law of motion, which is the law of inertia, it's simply talking about having net force equal to 0 newtons. So it doesn't mean, it doesn't mean that there's no force acting on the object. It could be like what I've said, a million of forces, but if the forces are balanced, then that object will continue to its state of motion. So if the net force is 0, then the acceleration is also 0 meters per second squared, which makes sense. Now, it also gives us the concept of equilibrium. What is equilibrium? Equilibrium is a state when the net force acting on the object is 0. So, when the net force is 0, then that object is in equilibrium. Okay, think about that. Equilibrium, from the word equal. So all the forces are equal but oppositely directed, so they cancel each other out and acting on the same object. Now, the net force or F net is 0 for equilibrium. Then acceleration is 0 meters per second squared, and the velocity is constant. So that's Newton's first law. So let's look into this one. So what is the answer? How much net force do we need to keep it moving in the same speed and in this direction? Correct. The net force is 0. Or simply, we don't need a force. because it will continue to move at its same speed in the same direction. If it's already in motion, that's what Newton's first law is talking about. If it's already in motion, you don't need to keep on pushing and pushing and pushing. Now, this is probably counterintuitive. Mrs. Nelson, how about when I have a ball, I push the ball on the floor and it will immediately stop? Well, not really immediately stop, but it will eventually stop. Why is that so? Well, then there is a net force. Then there is an unbalanced force for it, which explains the Newton's second law. So let's look at Newton's second law, which is the law of acceleration. So from the name itself, it talks about acceleration. What happens if there is an acceleration? So, according to Newton's second law, the acceleration of a system, so it's talking about a system, so it might involve two or three objects, is directly proportional to and in the same direction as the net external force acting on the system and inversely proportional to its mass. The equation for the law of acceleration is that net force is equal to mass times acceleration. Now, we can rearrange that. If we're solving for m, there's going to be net force over the acceleration. If we're solving for acceleration, it's going to be net force over m. Now, let's look into the last equation where A is equal to the net force, or F net, over m. So A is acceleration, so you can write that down. F is force, which is in Newton. M is mass, which is in kilograms. And of course, acceleration is meters per second squared. Here, it's talking about this statement of Newton's second law. It's talking about how acceleration is directly proportional to force. So what does that mean? If I pushed an object twice as I pushed it before, then that acceleration will be bigger by 2 times. So whatever change in the force will be the change in the acceleration because they are directly proportional. So look at the word directly proportional. What are these two variables that are directly affecting each other? Acceleration and force. So if I triple the force, then the acceleration will be tripled, which makes sense. How about acceleration and mass? So acceleration is inversely proportional. So the inverse, so by the way, this symbol right here that I'm drawing right here is a proportionality symbol. So if it's in the same and it's in the both in the numerator, then they are directly related. If one is in the denominator and one is in the numerator, then they are inversely related, which is on the second statement of Newton's second law. So the acceleration is inversely proportional to mass. So A and M are inversely related. What does that mean? Yes, mass, if I double my mass, then my acceleration given the same force will be half of the original acceleration. If I tripled my mass, right, then my acceleration will only be 1/3 because the heavier or more mass I have, more resistance, more inertia, then my acceleration will be lesser because they are inversely related. So if I decrease my mass by half, then my acceleration will be doubled. Okay? So hopefully you understand that well. All right, we're looking at Newton's third law. So Newton's third law is otherwise known as the law of interaction. So whenever one body exerts a force on a second body, then that first body experiences a force that is equal in magnitude size, right? And opposite in the direction of to the force that it exerts. So it involves two objects right here. One body, second body. So two different objects. So here we have in your open sack, it talks about a swimmer and the system of interest. So the system of interest in this situation is the swimmer. And the direction of acceleration is wants to propel forward, so it's going to the left. So here we can tell in order for me to propel forward, I have to kick using my feet on the wall. So force exerted by the the wall on the feet is towards to the left, and the force exerted by the feet on the wall is going to the right. So I'm kicking. So if I'm the swimmer, I'm kicking the wall to the right, and that propels me to accelerate forward to the left. So let's look at the free body diagram and what are these two action reaction pair is about. So the action is feet acting a force on the wall. That's the action force. So let's write that down. As a reaction to that, then the wall will exert the same amount of force on the feet, same magnitude but opposite in direction. Now, here is a free body diagram. So we have BF, which is a buoyant force because the swimmer is on the water. And of course, that buoyant force is balanced by its weights because it's not moving up or down. The swimmer is not sinking and the swimmer is not going up. But there is an unbalanced force, which is the force exerted by the wall on feet that propels it to that acceleration. So we see here that there is an unbalanced force, and that unbalanced force is in the same direction as the acceleration, which we just talked about in Newton's second law. Now, where is the reaction force? The reaction force is this, the force exerted by the wall on the feet. So these are action and reaction pairs. You're probably going to be thinking, why are these two forces not canceling each other? And if they cancel, then why would the swimmer go forward? Definitely not canceling, because if you looked at it, we have two different objects acting on two different things. So the feet on the wall, so the feet is exerting a force on the wall. Okay, think about that. And the wall exerting a force on the feet. So these two pairs are not acting on the same object. Just like a free body diagram, like what we do. So that's the reason why they don't cancel each other out. All right, let's look into some more examples. Hopefully, this will help you understand it more. So, for instance, we have an ice skater pushing on the wall. Okay, that's the action force. What would be the reaction force? The reaction force would be, it involves two objects. So, wall pushing back on the ice skater. So, you looked at it. It involves an object A, which is the ice skater, and an object B. And that reaction will be the force on object B towards A. So here, the action force is towards B. On the reaction force, the force is towards A. So there's two different objects that these forces are acted on or acted upon. Here are other examples of action and reaction. So look at these. When you're driving, your tire pushes on the road. So there's force object A and object B. So we always looked into the two objects because forces comes in pairs. The reaction would be object B doing or exerting a force on object A. So road pushes on tire. So object B acting on object A. How about a rocket that is propelling forward or propelling upward? So the rocket pushes on gas. So rocket is our object A, gas is our object B. Therefore, object B exerts the same amount in magnitude and size to object A. So that's the action and reaction, and hopefully in your quest homework you'll be able to identify the reaction pairs because there are some questions about that. Now, what are the big ideas for Newton's third law? So let's look at it. One is that forces comes in pairs. Okay. Second, action and reaction forces involve two objects. So you have to pay attention on that. Force on A by B and force on B by A. And I've gave you some examples of that. And of course, the last one, and which is very important, is that the forces that we're talking about in Newton's third law, or the interaction forces, are equal in magnitude but opposite in direction. However, they do not cancel because the forces are acting on two different objects. So hopefully you'll be able to write this down because these are big ideas for Newton's third law. What is the reaction force? So a book rests on the shelf of a bookcase. So we've got a we've got the action force, which is force of gravity acting on the book. So what object is exerting a force of gravity on the book? Earth, correct. So we say that there is a force exerted by the earth on the book. And that force exerted by the earth on the book is the force of gravity. Then the reaction, so this is our action force. So remember we started with, well, there's a force of gravity. Who's acting that force of gravity to that book? It's the earth, right? Because it's on earth and it's caused by the force of gravity of the earth. That's the action force. What would be the reaction to that? So look at your two objects, earth and book. So what would be the reaction to that? Force exerted by the book on the earth. Yes, there is a force exerted by the book on the earth. That is the reaction force. And of course, it is equal in magnitude but opposite in direction. So in other words, if the earth exerts 9.8 newtons per kilogram on the book, then that book will exert that same amount but opposite in direction on earth. So that's an introduction to Newton's laws of motion. I hope you liked it. So now you know why we have to wear our seatbelts all the time, every time we get into our car. And thanks to Newton's laws of motion, we understand why our motions are this and that. Thank you. Have a great day and be safe.